definition for the conservative force the definition for the conservative force is the work done, let it be your spring force. This is an elastic force. Elastic force, here we talk about spring force. The question here is that you have to prove that the spring force which acts along a spring is conservative in nature. That's the question. Now, one important aspect of a conservative force is that the work done by a force in a closed path is zero, then I can term that force as a conservative force. Please understand. The question is, you have to prove the spring force which is acting along a spring is conservative in nature. Conservative means you have to prove that the work done by the conservative force in moving the spring over the closed path should be equal to zero. If you can see, 1 second. Now look at this. Initially, boys, initially say the block is at position xi, right? The block is initially at position xi. You are applying a force, right? You have applied a force and then you started compressing your spring by applying a force on the block. Then the moment you apply a force, there will be a spring force acting in the opposite direction. You have applied a force on a block. Initially, the block was at position x1. You have compressed it so that it moves to the position x2. In both the cases, there will be a spring force. Once you leave the applied force, now what naturally happens is the spring comes back to its original position. So initially the spring was at position x1. You have moved it to position x2, and finally the spring comes back to x1. That is a closed path. Initial position is x1, final position is also x1, right? Now the question is, when the body moves from x1 and comes back to the same position, what is the work that is being done by the spring force? If the work done by the spring force happens to be zero, then you can state that your spring force is conservative in nature. I'm repeating this, boys. The block which is attached to the spring initially was at position x1. You have applied a force. The moment you apply a force on the block, there will be a spring force acting in the opposite direction. You have applied a force on the block. Now the block has moved to the position x2. So whatever work you have done will be stored as an energy in the spring at point x2. Then once you leave your applied force, all this potential energy stored will be converted to kinetic. Here all the potential energy now will be converted to kinetic. The block comes back to its original position. So when the block starts from x1 and comes back to the same position, if you can prove that the work done by the spring force is zero, then you can easily state that the spring force is a conservative force. So I think so. You started with the introductory part, boys. Have you completed this? Have you completed this?
Which diagram should we draw? Is it this one, ma'am?
Only one is enough.
Okay, ma'am.
So you can draw only this graph, sorry, this diagram. The other one, I just showed it for your reference. You have to prove the work done by the spring force, right? During one complete cycle in that sense, it starts from x1, and comes back to the same position. The work done should be zero.
Ma'am, is the applied force also a conservative force?
Yeah. Yes, boys. Provided there is no friction. The block is going to move over the frictionless level. Your block is moving over the floor. That floor should be frictionless. Only then you can state that your applied force is a conservative force. Okay, have you copied this, boys?
Yes.
So now what we'll do is, let us find the work done by this conservative force, sorry, by this spring force when your spring undergoes a very small displacement of dx. Again, I'm repeating, your aim is to find what is the work done by the spring force when the spring initially occupies position x1, moves to x2 and comes back to x1, one complete cycle. So what is the work done by the spring force when the body comes back to its original position? If you prove this work done to be 0, then you can say your spring force is a conservative force. So how to start with it? What we'll do is that we'll consider the displacement the spring is going to undergo. The displacement the spring undergoes is dx, whether it will be, let it be extension or whether let it be compression. When you apply a force, your spring is undergoing a very small displacement dx. Let us find what is the work done, and then we'll integrate between the limits. Copy down, boys. Work done by the spring force for a small displacement dx. Generally, we know for a small displacement dx, the work done will also be of a smaller magnitude. That's the reason you are representing the work done as dw. So dw is equal to the spring force into dx. So now what is,
Should we do a diagram?
yeah, at least one diagram is enough.
Okay, ma'am.
Ma'am, in the diagram, should we write x as dx?
No need, no need, no need. This diagram is for the initialization. That's enough. This is Fs, that's it. So what we'll do is that we'll find what is the work done by the spring force. See, you have applied a force. Immediately the spring will also apply an equal amount of force in the opposite direction. It'll try to move the object back. There is some displacement. So that displacement is dx. So the work done by the spring force for small displacement dx. Whenever your applied force is making the object to move to a displacement dx, immediately your spring force, right, will also do an equal amount of work in the opposite direction. That is dw is equal to minus kx dx. Have you completed this, boys?
Yes, ma'am.
Will the spring force be greater than the
Yes, I can't hear. Yes,
Hello?
I can't hear. Yes,
Your
Kritya.
voice is low. Now? Is it better?
So now, listen, boys. Now, if the block is moved from initial position x1 to final position x2, boys, if the block is moving from x1 to x2, suppose if the block started from x1, it is moving to x2. Let us find what is the work done. What, boys, we started with this, the work done by the restoring force or the spring force when the displacement was very small. It is Fs dx. So we had got this expression as dw is equal to minus kx dx. Now the question is, when the spring moves from initial position x1 to final position x2, what is the work done? So work done is equal to integral dw. So it is minus kx dx. Your x is varying from x1 to x2. Is that clear, boys? Because you're learning the integral calculus right now, that's what I'm repeating it. See, the work done by the restoring force when your spring is moving or the block is moving from position x1 to x2. This is the work done. dw is the work done when the spring undergoes a very small displacement of dx. Now, what is W. W is the work done, right? Total work done when spring moves from position x1 to position x2. Now, how will I evaluate this integral? So how will I evaluate? What is general equation? X dx will be equal to x squared by 2, correct? So now look at the, I don't know whether it's getting confused for you. So minus k is a constant, boys. So anything that is a constant should be brought outside the integrand. So this becomes
Oh, why is
x.
it minus integral kx dx?
No, because what was dw? What was the expression for dw? dw was minus kx dx.
Oh,
check.
yes, ma'am. Yeah.
Okay, so that's the thing I'm substituting. K is a constant. Okay. This is x dx. Is that clear, boys? Okay. So now minus k into, if I evaluate this integral, it becomes x squared by 2, correct? And the limit should be x1 to x2. But is this clear? 11b.
Yes, ma'am, it's clear.
Okay, fine. Now let me substitute. Your x is going to take a value x2 upper limit, and then it takes a value of your lower limit. So I'm getting this as this one, right, boss? So minus k into x squared by 2. It has to go for a lower limit, upper limit 2 and lower limit 1. So I'll put this as x initially takes the upper limit. Sorry, this is x2 and this is x1. So it will be x2 squared divided by 2 minus x1 squared divided by 2. Is this you're getting, boys? This is the work done by the spring force when the spring moves from initial position x1 to x2. Are you clear with it?
Yes, ma'am.
Okay. Now the question is, where we started, we want to find what is the work done by the spring force when the when the spring started from x1, moved to a position x2 and comes back to x2. That is what we wanted. Was this is the work done by the spring force. The last expression what we have got. Right now, net work done over the closed path. This is the work done when the spring is moving from x1 to x2. This expression. Now, what about this? What is the work done when the spring moves from x1 to x2 and then again to x1, full complete path? Okay, so once again, I'll just go for this. Work done. Where you had minus k, so minus k x2 squared by x1 squared minus x1 squared. This was 2 and this was this when the body moves from position x1 to x2. This is what we got last derivation.
Ma'am, could you move that thing?
We cannot see it. We can see ink in on it.
No, you can't see. This PowerPoint is not visible, boys.
Ma'am,
No,
it's stuck. Stuck, ma'am.
And the Microsoft PowerPoint want to keep your ink annotations, ma'am. Just close that.
1 second, it's not working.
It's stuck, ma'am.
Slide. One second. Now, is it fine for you now? Can you see the slide? I've put a new slide.
No, ma'am. It's
No,
the
ma'am.
same.
No, ma'am.
What has happened? Now, can you see the slide? Can you see the slide?
Yes, ma'am.
Yes, ma'am.
Okay, wait one second. Can you see the empty slide now? Can you see the empty slide?
Yes, ma'am.
Yes, ma'am.
Now, I'm just redoing this work done by the spring force, right? When your object moved from x1 to x2, your object has, the spring has moved from x1 to x2, work done is equal to minus k into x2 by. Now, can you see this, boys?
Yes,
11
ma'am.
Okay, fine.
Yes, ma'am.
This was when the body started from point, spring started from point x1, it moved to x2. Now we'll go for what is the work done in a closed path. Work done by spring force in a closed path. In a closed path means it has to start from x1 and it has to come back to x2. So initial position was x1. It moved from x1 to x2, and from x2 it is now moving back to x1, right? So now what happens to W? Lakesh? Lakesh? Lakesh?
There was no one. There's no one.
Um,
Oh, sorry, boys, it's 11. Sorry, I was just calling 11C. Harish?
Yes, ma'am. Yes, ma'am.
Harish, in this scenario, right? Look at this expression and what should I replace this x2 as?
With x1 because
Yeah,
you find
x2 should be replaced by x1. Boys, are you clear? Right, in the previous expression, x2 was the final position, correct? In the previous, this expression, whatever I have highlighted, x2 is the final position. But for this scenario, in the next scenario, what is your final position? What is the final position of the spring?
X1.
X1. So in that case, this x2 should be replaced by x1 squared by 2 minus x1 squared by 2. Or should I redo the integral part right now? Should I redo the integral part?
No, ma'am. Understood.
No, ma'am.
no, ma'am.
In case 1, this is x2 was the final position, x1 was the initial position, right? So x2 represents the final position, x1 was the initial position. Now look at the second scenario. X1 was the initial position, final position is also x1. So that, can you see this? In the previous case, x2 was the final position. In the second case, x1 is the final position. So I've changed. But initial position in both the cases are the same. Now, what happens to this value? The work
0.
done by 0. So the work done by your spring force in a closed path means initial and the final position are going to be the same, is 0. Then what can you say about the spring force? What can you state about the spring force?
And spring
What type
force is
of
conservative.
Conservative.
Conservative. That's the thing. So after this, W is equal to 0, then what statement you have to write is, we can conclude that the spring force is a conservative force.
Ma'am.
Hmm.
Ma'am, why are we doing integration? We can write that the displacement is 0.
Displacement is 0. You can do that. There is no harm, but The thing is that integral calculus has been introduced. You have to work in this way, boys. And why integral? Wait. One more question. That's fine. What you have asked, you can go for your displacement as initial and final are the same. Just put the W is equal to Fs cos theta. That's what you mean. Boys, here your force itself is not. It's not a constant force. It's a variable force. See, when we introduced your work done, if it would have been a constant force, then I could have used W is equal to Fs, work done is equal to F into Fs cos theta. Now, why is that we went for integral calculus? We went for integral calculus when your force acting on the body was not a constant force. Are you clear, boys?
Yes, ma'am.
If the force acting on a body is a constant force, then W is equal to F into S. If the force acting on a body is not a constant force, if it is a variable force, I cannot use W is equal to F into S. What should I do? I should integrate, because the force keeps on changing. If the force changes, your displacement also changes. That's what you will put the limits x1 to x2. So your force kept on changing. If that is the case, then your work done can be found only by the method of calculus, that is integral calculus.
All right, ma'am.
So things is not stopping only here. What we have done is, first part, you have proved that the work done by the spring force in one complete cycle is 0. So you have proved that the spring force is a conservative force. Next, what is very important is that you have to find an expression for the elastic potential energy. Boys, I'm going back to gravitational potential energy. Suppose a body is lying on a table, right? You apply a force and lift the body to a certain height. So whatever work you have done against gravity will be stored as an energy in the body. Such energy we call it as gravitational potential energy. Your potential energy is of two types in mechanics. I'm talking about mechanics. Your potential energy is of two types. One is gravity. Whenever you change the position of the body, immediately whatever work you do in changing the position of the body with respect to ground, that will be stored as an energy. We call it as gravitational potential energy. Elastic potential energy, whenever you change the shape of a body or dimension of a body, when you compress a body, or when in the case of a spring, when you extend a spring, in all these cases, whatever work you do will be stored as an energy, and such energy we call it as elastic potential energy. The best example is your bow and an arrow. When you place the arrow, now you're changing the shape of the bow. The moment you change the shape of the bow, energy will be stored, right? And that potential energy will be stored in the bow. Was you have a bow and arrow arrangement. When you keep an arrow, you're changing the shape of the bow. Whenever the shape of the bow is being changed, and energy will be stored up in the bow. That is what we call it as elastic potential energy. The moment you leave it, all the potential energy stored in the bow will be transferred as kinetic energy to the arrow. That's the reason the arrow moves forward. That clear, boys? So now what we have to prove is that we have to find an expression for elastic potential energy. For gravitational potential energy, it was mgh. Now I have to find the expression for elastic potential energy. Before that, yes, boys?
Ma'am, can you show the previous two slides for 1 minute? Ma'am, the one before this. Oh, thank you, ma'am.
Right, boys. Plot a graph between applied force and displacement. This is now applied force, not the. Because this is the applied force. You have a spring. You are applying a force. So this will be the direction of your applied force. What will be the direction of the displacement? Same direction. Right? Your Hooke's law states F is proportional to S, sorry, here we'll take it as X, or F is equal to K into X. So if I plot a graph between F and X displacement, it will be a straight line graph, linear graph. The slope gives you what? The slope gives you, but can you say what does the slope gives you in this expression? Maths, you have, you're learning your maths, you have plotted, even in grade 9, 10,
Yes.
you're plotting. How do you find the slope? You know what is y is equal to
Tan
mx plus, okay, no, it's correct, tan theta. You know what do you mean by y is equal to mx plus c? What
Yes,
is
ma'am.
y is equal?
Yes,
What
ma'am.
is that? What does it represent?
Ma'am, the y-intercept.
Y, y-intercept? No. That is representing y-intercept. 1 second.
Ma'am, M represents the slope.
Yeah. Then what does y-intercept represents? Okay, 1 second, boys. I have to just like a bit of mathematics. Y is equal to mx plus c. If I have y versus x graph, clear, boys, right? Now, what is m? If I have a graph, this is the graph. What I'm getting is your graph. Just mark this as. This is what you say y is equal to mx plus c. Here, the slope of the graph is represented by m. Now, this is called y-intercept. Intercept in that sense, look at the graph. This graph is going to strike your y-axis at some point, right? And this value, we call it as y-intercept. Because we have a graph y versus x. This way also, boys. I can have, sorry. I can have a graph like this. Or I can have a graph like this. Now, this part will be y-intercept. Here it will be negative. Here it will be positive. So this is an equation of a straight line, right? This will be an equation of a straight line. You all would have learned, right? You all would have learned. Okay, y is equal to mx. X-axis. What is your y-intercept here, boys? What is your y-intercept? C, the value of C. 11C, sorry, 11B. What is the value of C here? Where is this line going and hitting the y-axis? Does it go and strike the y-axis? Boys?
Yes.
It strikes the y-axis. Okay, if it strikes the y-axis, you tell me where, at which point does it strike the y-axis?
0,
Zero.
C.
Yeah, it's a 0. That is why this this straight line will be represented as y is equal to mx, where this m becomes the slope of the graph. Are you clear, boys? So when you learn your mathematics, take a little bit of additional care, because whatever you learn will be applied in physics. Okay, boys? Right. Now, applied force versus, boys, I am just writing applied force. F applied is proportional to the displacement, or F applied will become equal to K into X. F applied is along your y-axis, your displacement along your x-axis, y-intercept is not there, right? So that's the reason the slope is represented by K. Now, boys, in the beginning, we started with this. I can find the work done by using the expression F is equal to, sorry, W is equal to Fs, or I can find the work done by finding the area under the graph. Yes or no?
Yes.
Yes, ma'am.
So now, same way, I can find the work done by the applied force in stretching the spring. Suppose if I apply a force and stretch the spring, whatever work the applied force has done will be stored as an energy in the spring. Your aim is to find what, boys? Your aim is to find the potential energy of a stretched spring. How do you stretch the spring? By applying a force. This applied force is doing a work in stretching the spring. whatever work the applied force has done on the spring will be stored as its energy. Now, how can I find the energy? Energy is nothing but the work done, right? So, how can I find the work done from force versus displacement graph? It is only the area under the graph. Is that clear, boys? The area under the graph gives you the work done. So what will be the area under the graph? It's a triangle. Half base into height is.
Ma'am, should we write this?
Yes, you have to.
Oh, okay, ma'am.
But look at this graph. It's a method A. What is work done? I think so. Leave this. I'll just put one more statement over here. What is work done? Work done is equal to area under the graph.
Yes, ma'am.
So that will be base into height. Base is x. Height is, you know that spring for applied force F is equal to kx. You need not write all these things. This is more than enough. So kx into x. This work done is stored as the potential energy in the spring. So how will I write the potential energy? The potential energy of the spring is half kx squared. 11b, is it tough? 11b. Prasanna. Yes. Is it tough?
No, ma'am.
Yusuf.
Yes, ma'am.
Zuhair. Zuhair. Is it fine?
Where is
Siddharth.
absent?
Oh, sorry. Siddharth.
Yes, ma'am. It's fine.
Potential energy is equal to half kx squared. This work done is stored as the energy in the spring. We call it as elastic potential energy. Only thing left in elastic potential energy is graph. So when I'm doing the graph, you just be a bit careful, boys. Because you should understand the graph properly. Boys, do I have time to go for the graph or?
My period over.
Okay, fine. So
Period.
graph, I'll do the graphical part tomorrow, then I'll start with collision. So collision will be the last part. After collision, bit of par. Par you have already learnt in your grade 9. Okay, thank you.
Ma'am, can we do numerical tomorrow?
Huh?
Can we do
was?
numerical tomorrow instead of theory?
Theories,